Great. Welcome, everybody. So, in many ways, you can think of today as the last lecture, in the sense that we're going to try to wrap up what we've been working on, what we've been trying to understand. And then tomorrow, mostly will be, the first lecture will be kind of applications, how you can use the techniques that we've used to prove theorems that, you don't need to get black box these and then use them to prove stuff. And then the second lecture tomorrow will be a bit more open-ended on things that may be for the future or something like that. So that also is saying, in a way, please ask questions of the things that you didn't fully maybe crystallize yet, so on and so forth. So I mean, you can also ask them tomorrow, but the main math content is going to sort of end up today in a rigorous manner. Does that make sense? Okay, so also some of you have been asking me questions, and I think it's a good moment also to just sort of pause and follow Melissa's advice. So pause for 10 seconds. Where are we? So let's do a very quick review of where are we. All right, so I want to make clear what depends on what. So the first thing is we have a Legendre mean lambda, which lives in this case in a contact 3 manifold. And out of that guy, we extracted a category, sheaves sub lambda of R2. In practice, we computed these people via the exogamy description, and we ended up talking about representations of posets, linear algebra problem, flags. That's how we determine the sheaf. So again, if we have a problem with some interesting Legendre knot, maybe that's a very simple one. But here you put the vector spaces, so on, and you get a number of sheaves. In this case, you get 5 lines in C2. Does that make sense? Okay. Now, out of here, you can name a space. And the space that you can name is the space that for now I've been calling M of lambda. And there is also a pointed version of that, which is M lambda T. Okay. So what this space does is it geometrizes in an algebraic geometric way isomorphism classes of objects in here. To be precise, isomorphism classes of objects on the pseudo-perfect objects of the category of compact sheaves. That's a technical thing. But intuitively, it's exactly doing this thing about 5 lines, pairwise distinct, so on and so forth. Are we okay with that? So I'm using blue here to be clear that this space, the ambient space we're dealing with, this manifold that relates to brain varieties, depends on lambda. L, a filling, has nothing to do yet. Okay. So the next step is to incorporate here the data of a filling. So now you have L, a filling that lives in T infinity of R2, standard reveal contact structure, the kernel of the restriction of which would be this contact structure, and you want this to be a filling. And the way you do that is essentially by saying that lambda is the boundary of this L. And again, think of this contact manifold as the boundary of this. Now, does that name a category? Yes. If the filling is exact, it lives to a Legendre, and it names a category in here. What is the category? It's the category of sheaves on now R3, which is where the Legendre lift of this Lagrangian lives. Yeah, when you use the notation L fiddle, I'm against twiddles. I don't like to. It's just bad notation. I mean, I'm not saying when you want to use it, but I like L up. Okay, to indicate we're lifting it up. So these are sheaves singularly supporting an L up, and the Legendre lift of that guy is going to live in R3, which is really these are 2 times R. Okay, are we okay so far? Now, what happens is that in this particular case, when we're setting this particular category, this guy, when you unproved for you, that was isomorphic to local systems on L. Okay, so that didn't happen here. This is not local systems on lambda, but because of this open condition at the end, effectively, that's what was happening for the Lagrangian field because of the embeddedness. Think about this doesn't have rep chords. If you don't have rep chords, you get local systems. And the information of the rep chords is what makes this category kind of interesting. Yeah. So when you have local systems and you now translate down to the category, from the category to the modalized space, here you're going to get local systems of lambda as a subset there. And so, for instance, if you take, and that is your choice, so for instance, if you take, and we are taking local systems with the principal group GL1C, So these will be local systems which are abelian, local systems whose stock is just K. Then here you get local systems of rank 1 on L, but that is the same as morphisms from phi 1 of L into C star, and that is the same thing as this cohomology group. So really think of these as local systems of rank 1 on L. And I apologize for using the same notation for the category in its derived stack. Usually I use like mathfrak for these or something. But so one is the category, the other is the actual space. So that is the intrinsic description of this. And this is what we typically denote, forgetting a bit where this came from, the model, the torus. So this is the open torus that we've been talking about, and that I've been denoting purposefully tau sub L. Okay, so this is the tau sub L inside of these, and this is an open inclusion. Why is this an open inclusion? When Yuan say in his talk, he said that there was a fully faithful functor from this category to this category up here, and that fully faithful functor induces that inclusion of the derived steps of the spaces. Yeah.
So implicitly assume L is embedded. But if it was unobstructed,
in this case, yeah. But what's really important is that it's exact. Yeah, if it's unobstructed, you're also going to get that. So I'm going to talk about it in the second tomorrow. But if it's embedded, it's obvious what local system is. And now the question is, what is the local system on a on an immersed surface? Yeah. And the answer is interesting. Let's just say that. But appropriately understood, this whole thing works for immersed fillings. But you gotta understand what is a local system on an immersed surface. Does that make sense?
What does one refer to?
You're using GL1. Oh. Like you're going to have local systems with like GLN. And then in here, the chart would be the character variety of that corresponding thing. But I'm trying to make things like as simple as possible, and here the character variety is different. Are we okay with so far? Okay, so now we keep adding data to these things. Again, always guided by the geometry. You have D, this L compressing system for L. L compressing system for L. And just to move things forward, I'm going to for a second skip on what goes here. So there's some categorical interpretation of this, of what buys you at the level of this categorical interpretation. You're welcome to ask me. When you on, we wrote it in a paper, kind of, something to do with Cauchy homology or blah, blah, blah. Anyway, let's not get there. What I was telling you this morning is that these L compressing systems gives you a function, a set of functions called A sub I, and these are the merodromies around the boundary, so merodromies along the Poincare dual of the bases given by, assume this is a maximal compressing system, the Poincare duals of the boundaries of this. Okay? And now what's really important, and I cannot emphasize this enough, is that these merodromies, as they are defined, each of these AIs is a function which, the way it is built, it's only obvious that it's a function on T star T of L. It's only a function on that torus chart. And by the way they're built, also, you know, this is non-vanishing. So it's a non-vanishing function. Another way to say it is that what these coordinates do for you is they choose explicit isomorphism between the group ring of between the functions on the torus and the Laurent polynomials on these functions. So this is exactly this isomorphism. You see? Like given a torus, I could coordinatize it in many ways. The same way that, you know, the plane, you could say it's the spectrum of polynomial rings in two variables, x and y. But I could change variables and have some other variables, like x comma x plus y. I mean, it's perfectly fine change. So these coordinates, which are the merodromies around here, really are only functions that are obviously all right in here, and being non-vanishings, they actually form a basis for you. Okay. And what's sort of spectacular about this business is this thing really seems to be very canonical, like have very nice behaviors. So now I'm going to draw everything in a picture. So in a picture, it looks like that. This is my space in here. This is my space. This is my space in here, M modalized space of lambda, M of lambda t, again, spaces of lines and flags and so on. And now, kind of cartoonishly, here, a Lagrangian filling defines for me an open torus chart. Cartoonishly, because this is a risky, so it's a risky dense. Like it's this chart here. And then, maybe cartoonishly, but what these guys are doing, I didn't do it on purpose. So this should have been in red. This is the chart given by this red line here. Tau sub L. And now the merodromies, which are these things in green, quote unquote, you can think of it, they're giving you a basis, a particular set of coordinates in here. So this is A1, A2, A3, so on and so forth. All right. Now, the goal of this lecture, or one of the main things that I will start talking about right now, is since we actually have the L compressing system, it's not that we just have the variables. We actually have this geometric piece of data. We can do Lagrangian least surgery. Therefore, we can implement a Lagrangian least surgery on L, and the idea is that you're going to get to another chart, T sub L prime, T sub mu of L, and it's going to have some other variables A. And I'm going to now tell you how those change and how it leads to the notion of cluster algebra in this viewpoint. Is this scheme, I don't know, I could probably do it better, but it's a pretty good summary of what has been happening so far, if you understand every word.
I have a question about the base points.
Yeah.
So from the notation, it looks like you only inputted that at the very last step when you build a quantized space.
No. Yeah, sorry. That's up here.
Okay, so she does know about that data.
You can name two categories, one without the base point and one with the base point.
I was just focusing on one of these such choices.
Yeah, I typically choose one base point per component, and that's it. That's something you can say canonically. One base point per component, and that gets you like the right answer.
Thank you.
If you have more, you get what's called frozens. Okay, so now fundamental theorem of this Swift calculus, part 2. It's exactly about those coordinates. Fundamental theorem of Swift calculus. And indicated part 2 now. Is that this modelized space, the structure that its ring of functions has is particularly good. So remember that I told you that this guy was an affine variety times BGL1. Let's for now, please just ignore the BGL1. It's a completely trivial factor. So let's just think of it as an affine variety, okay? So this is affine understanding it's affine times a stack, trivial stack. Are we okay with that? Now, if it is an affine variety, we can take its ring of regular functions, and that is a commutative algebra. Not BG, not anything funny. It's an honest commutative algebra, period. So the fundamental theorem says that the ring of functions of that variety, in the case of lambda beta, for the base points, which is 1 per component, is a cluster algebra with cluster seed given by that data. The cluster algebra with initial seed given by a filling L and L compressing system. The L compressing system D. And I'll be more precise as I start discussing this statement, L compressing system D. And this D, I'm not going to specify that, but in this theorem, and while I'll discuss this is always obtained via the construction I explained. So this is all obtained via Lustig cycles. So that statement is the L compressing system coming from Lustig cycles, okay? So this is from the Lustig rules that I introduced before. All right. Now, if you don't know what a cluster algebra is, this makes no sense. It doesn't give you much information, but I want to convey the two main things that are used in order to conclude this, and really the two big things that this is including as a statement. Angel, you got a question?
Yes. So is this statement saying that the range of regular functions of the variety associated with the exact cluster?
Yeah. So sorry. So this is exactly the X beta variety from yesterday. Make that clear. This is isomorphic to the variety X beta great variety. So when I talk to, when I go to conferences, I was doing a mini course on these guys, on this model of sheaves about Legendrians at BAM for 3 days with quiver people and algebra people, and I never said the word sheaf or somebody was there, Ursula was there, right, James? I never said the word Legendrian or filling or anything. I just talked purely about braids and that, and I use the language braid varieties when I'm sort of in that mindset, or theoretical, annually group. And otherwise I would call it this. But you're in the middle, so I understand your question. In this case, they are the same. Okay, so what is this cluster algebra business trying to tell us? Like, what are the good ideas that this theorem is telling you? So in particular, like that. So in particular, so the following two things are implied by this, but really you need to prove them before you prove this. So this is equivalent kind of in a sense to that. The first thing is the functions AI, so the merodromies AI are globally regular. Which is to say, i.e., I am not just a function on the torus chart. It's not something that I can only define on the red torus that maybe has a pole in here. No. It's something that actually doesn't have a pole in the entire variety. So i.e., each a sub I is a function on that space. And in fact, more is true. And they stay that way, they are regular after any, in fact, it suffices one, but after any one Lagrangian dissurgery. So not only is it true that when I start with a filling and I get this torus chart, you can name with the L-compressing system these functions in here. These functions apparently, I mean, think about it for a second, right? Like, even if you just think about monodromies or merodromies. This is something that's completely obvious for your filling. Now, start to do Lagrangian dissurgeries. Where on earth does your curve go? I mean, you have no idea how to name it canonically, right? Like, if you were taking, oh, it's the monodromy around this, and now you start to do Lagrangian dissurgeries and everything. When you look at it from another filling, that curve doesn't bound a disk over there. It has no reason to not have a pole or not vanish or anything like that. And it does vanish typically. But the theorem says it doesn't have a pole. It will stay regular. And in fact, you start with this one, you mutate Lagrangian dissurgery in any of the disks in the compressing system. The statement is that does stay regular in. And there's a slight improvement of this statement, which is that it not just only stays regular, but you can exactly say how it changes. So under Lagrangian dissurgery, this surgery, which is what we discussed kind of at length yesterday, at this P sub k, this k is going to be that k at some point, and that a lot more name. So at a given k that I choose inside of my L-compressing system, if I surgery them, then the following happens. The new variables mu sub dk sub a k, well, I should say it like that, sub ai, that variable does not change, stays exactly the same if I is different from k. So what I'm saying is all the monodromies stay exactly the same except for one guy. And the one that changes is exactly the monodromy associated to the disk you're compressing. And now comes the kicker. The mutation formula, the way the monodromy changes, is as follows. A sub k, the new one is going to be divide by the old one, a sub k, and then take the product over all the AIs such that something, and the product over all the AJs such that something. And what is the something? the something is, this is the product over the AIs such that the boundary of DI intersects the boundary of del K positively. And this is the people such that the boundary of del J intersects the boundary of AK negatively. Okay, so let me draw it in a picture. So here you have your Lagrangian filling, L. The Lagrangian disk at which we're mutating, let's draw it for a second in green. So you have this dk here, dk. The boundary of dk is this curve in here. And now you're going to have other disks coming through here. Some disks coming through here, they're oriented, and another disk may be coming through here, and that's oriented the other way. So these positive intersections, say, depends how oriented green, and this will be a negative, definitely opposite side from this one. So what I'm saying is, all the variables that come from intersecting negatively contribute in a product, and the other ones contribute in a product in here. And in fact, they not just contribute as is, they contribute exactly by the number of intersections. That's the number of intersections between DI and DK, and same here. DI and DK. So for instance, if for some reason this orange came back and intersected the green again positively, I would have a square in here. So that's the magical formula. That's something that you prove purely with symplectic topology. You just go compute everything, and I'm going to explain how this theorem is proven in the rest of the lecture. But the point is, you get this formula that tells you exactly how the meronomy changes. You use this formula in order to prove that these are regular after one mutation. So you first prove these ones are regular, then you prove this formula, then you prove that they're regular after a mutation, and then you use these two things together with something I'll tell you about later to prove that these. And
so the listing formula, the rules give you cycles, but they aren't oriented. There's no canonical orientation. Is that correct? So
you choose the orientation of the plane.
Choose the orientation of the plane. I see.
Yeah. So yeah, in a way, yeah, there is the orientation of the plane that you use. Yeah. In a complex setting, it really is like that because it's C, so it's oriented already like that. So that's why I use that. Okay, questions on Roman.
Yeah, for monotomous, do you get X variables?
Yes. Yeah, exactly. Yeah, well, I'm gonna get there in maybe 20 minutes, but this is called the cluster A mutation formula. And there's an analogous thing called the X mutation formula. And that's what you would get if you were computing X variables. For instance, in the X variable mutation, Xi goes to 1 over Xi. That's exactly what you get for the monotomies. Say the cross ratio. Yeah.
Sorry, how does like mu decay of AI then?
So this is okay. So mu decay of AI is you have your compressing system, you pick the disk decay, you do a Lagrangian disk surgery along that one, and the old compressing system goes to another L compressing system. Now I'll talk about it a bit later when we're arguing the proof of that, but for now let's just take it as fact that the L compressing system before goes to the new one. Now, in the new one, the disk that you contracted is now this new disk, kind of dk prime, and the other disks kind of go through that. I mean, you can imagine that a disk that has nothing to do with that one just goes through easily, and the others, there's going to be some interesting geometry. Now, once you've gone to the new system, now you can do Poincare dual of those disks and take merodromies. That's exactly what this means. This is the merodromy of the Poincare dual of dk prime after Lagrangian disk surgery. All right. Okay, so the rest of the talk is essentially like making sense of all of these, why it's true, intuitions, examples, so on and so forth. Is it clear where we are? Okay. So now I'm gonna talk purely about combinatorial algebra stuff for about 10 to 15 minutes. What is a cluster algebra? And then we're gonna link it back to everything we're doing. Now, the first thing to keep in mind, and the thing that gets you through the algebra, or that gets me through the algebra, is that given an L compressing system, you don't just have a bunch of curves in a surface, you have a bunch of curves in a surface whose H1 has a skew-symmetric intercept.
Sorry, I have a question. So in this formula that you got there, is this like a generalization of what James just showed earlier?
No.
Or
I mean, he did one case for the two-stranded, you need a mutation.
Yeah,
What?
but are you asking about how to compute the cluster?
yeah.
Yeah, so that's how to get a regular function from the we.
Oh, from the ones that you.
That's how the correct function transforms.
Okay, okay.
Yeah, yeah, I mean, like, how does that work? Like, historically, you compute, and you start to see that everything is a polynomial. You start to believe these things are gonna be regular, but you don't wanna use that hideous, I can say, but hideous algorithm to compute those guys. You wanna first prove the regular sort of conceptual level, and then you wanna have a computable way to like get to them. But one first prove they're regular, sort of other principles, and then at the end, you say corollary, they're polynomials because of these other reasons.
Okay, so just to see if I.
Yeah.
So then what James showed is how you construct the eggs.
Yeah, it's like in practice, how would Dapping's app or how would a computer implement the algorithm? I mean, there's a whole section in the paper in section 5, in that paper explaining the algorithm that James explained, and that's sort of explaining how to compute these people.
Okay.
Right. Okay, so the thing to keep in mind as I start to talk about quivers and combinatorics, keep in mind that these, there's collections of disks, give a skew-symmetric matrix which is exactly the intersection form. So that's the intersection form restricted to them. Are we comfortable with that? I actually don't know if that's a catcher, but in H1 of a surface, there's an intersection pairing in dimensions in which the half dimension is odd, that's skew symmetric, or for manifolds it would be symmetric. And you take that intersection form, that's just something abstractly defined in terms of standard intersections. You have two cycles, you can transversely perturb them, so we can transfer intersections, generically perturb them. And once you have this skew symmetric form, which is abstract, if you have a basis, you can write it out as a matrix. So you get a matrix. Another way to say that, equivalently, this is the information of a quiver. Equivalently, a quiver. And I'm gonna denote this quiver Q sub D. So what is the quiver saying? The quiver has as vertex I of the quiver, that is exactly the boundary of the I. As vertex J of the quiver, that's the boundary of DJ. And I'm gonna put as many arrows as intersections I have. So this is an arrow, and you weigh it, you say 2 arrows, 3 arrows, by the number of intersections. So be fully precise, it's this intersection form between DI and the homology class and DJ. Because this is skew symmetric, notice that that's not the same as the number of arrows from J to I, it's minus that number of arrows. Does that make sense? So in here, purely from an algebraic viewpoint, this would be such that if you have an intersection point which is positive and one that's negative, you would have no arrows in there. That's what the algebra would tell you, right? Skew symmetric matrix would have a 0 because you're computing algebraic intersections. Comments on that. This is going to become a problem because we're doing geometry, so we have to distinguish geometry from algebraic intersections, and that's such as my paper will come out of the second one. Okay, is this information clear? The combinatorial one. Okay, so now just quivers. There is no surface, no surplusage geometry, no anything, no Lagrangians, quivers. So let Q be a quiver. So a quiver is a directed graph, and we're going to assume that it has no loops and no 2 cycles. So you don't allow a vertex with an arrow to itself, and you typically don't allow 2 vertices with an arrow this way or an arrow that way. You can allow it, but you're going to cancel these kind of things because you're thinking 1 and -1. Okay. Given a vertex, so given a vertex K of the quiver, we can consider an operation that Fomin and Zelevinsky introduced in 2000 called quiver mutation on a vertex K that produces another quiver for you. So we can consider what's called the quotations, it's called like that. I'm just trying to emphasize mutation of Q at the vertex K. So I did write, yeah, that's the moment. I did write the general mutation rules in there, so if you forget them during the talk, you can go with that. I'm gonna do an example, but essentially what you're doing is, the first, it has 3 steps. The first step is you look at every arrow coming from another vertex to K, and any arrow from K somewhere else. And then what you do is you add, and that's the arrow in orange in there, you add an arrow from the vertex that was incoming to K to the vertex that was outcoming to K. And maybe there's 3 of them, you put 3 of them. Okay, if there's 7 entering and 5 exiting, then you put 35 of them. Okay? Once you've done that, you take K, and every arrow that was inwards, you make it outwards, and every arrow that was pointing out, you make it point in. So you reverse the arrows that are exactly incident to K. Note that none of the arrows in orange matter here, so steps 1 and 2 are kind of interchangeable as long as you add the arrows orange in the right direction. Okay. And then finally, this process will create 2 cycles. It will create, oh, that arrow is the arrow. Dan, can you reverse the second arrow in the 2 cycle over there? Yeah. Talk about engaging the audience. So every time you have a couple of arrows like that, algebraically, this is the Fomin-Zalevinsky algorithm, you delete it. Okay. In geometry, that's a crime, I would say. And indeed, the subtlety between symplectic topology and cluster algebras very much lies in being able to cancel geometrically. If you knew you could cancel algebraically, which is always kind of an interesting challenge. So let me do an example in here. So for instance, suppose that I had the quiver given by, let's call it the D4 quiver. So that's my vertex 1. I have my vertex 2 in here. I have my vertex 3. I have these 2 arrows in, these 2 arrows out. So that would be my quiver Q. For kicks, that's the kind of quiver that you get for the 3-3 torus link. So you know, it's called D4 type, nothing to do with the D4 minus, kind of I think it diagram. Let's say mutate it at, let's make it interesting. Mutated at 1 will produce something. By the way, just so you get a quick sense, if I mutated at 2, things are really easy. At 2, step 1 is trivial. And then you're just going to flip this arrow. So when you have something like a leaf of a tree, mutating there just flips this. Mutation here flips this, and mutation here will flip this. That's why I'm choosing 1, because it's the other one's really easy. Okay, so what would happen? You keep exactly the same vertices, and notationally, you also keep the same notation. So in here. And now the new arrows are going to be what? Well, there's going to be a new arrow from 2 to 4 coming from concatenating these and that. That's this arrow over here. Then there's going to be one from 3 to 4 coming from over there. And now I reverse every arrow that existed that was incident to the wall. So this is my new. Do I see any 2 cycles? No, so I don't need to do step 3. And that's the deal. So it's a somewhat violent operation. I mean, it's not completely out. They discovered it for a reason. It's a very beautiful story. I can tell you sometime later. But it comes from somewhere. By the way, topology should have discovered this because that's essentially the Casals Lecture for. But I'm going to tell you something. Okay, so that's going to mutate up 1. So that's the combinatorial underlying, the combinatorial skeleton of a cluster algebra. The combinatorics that go into the cluster algebra are precisely quiver mutations. Now, how do you get an algebra out of that? Here's what you do. A cluster algebra is given to you as a bunch of generators. You just say it's the algebra generated by these people with these relations. A really wonderful way to give an algebra is to give generators and relations. Same with a group of generators and relations. The tricky stuff is that there's going to be infinitely many generators and infinitely many relations. And you don't typically know that you can make it out to be just finite generated. Sometimes yes, sometimes no. So here's what you do, is you put variables, and usually they're called x1, x2, according to the vertices, x3. So you put, for each vertex, you put a variable in there, and this is purely formal. There's no geometry, these variables mean nothing to them, I mean, from that perspective. And now, when you change in here, you're now going to change according to a certain formula, which depends on the quiver. So the change of variables for your initial set, x1, x2, x3, x4, depends on Q. And for any vertex that you choose on Q, you get a new set of variables. Does that make sense? Okay, so first of all, let's for instance, okay, maybe I will just tell you, if you mutate at K, so the variable K that comes from mutating, so this is the variable at the vertex K from mutating at K. So in here, x1 prime would be the variable here, that would be x1 prime, x number 1 prime, from mutating at vertex K, it's going to be exactly that formula. Okay, I present that formula because of geometric reasons, but the reason is the product of these two people are going to be people i's for which there's an arrow into K, and those are the xi's, and then arrows for which there's an arrow out of K, and then those are going to be, maybe I should say, the number of arrows from I to K, and this number of arrows from K to J, and this stage. So that's the A mutation formula, A meaning capital A, not A, like the A mutation formula, okay? And that tells you how from this set you go to that one. So for instance, x2 stays the same, x3 stays the same, x4 stays the same, and now what you know is that x1 prime is going to be x1 at the bottom, and then whoever was coming in, so say x2 times x3 plus, and now x4 in here. So that would be the way in which the new variable is. So here's how you construct the cluster algebra, and this is by definition, which is a highly non-local definition. Is you take any quiver you want, the cluster algebra associated to the quiver is the algebra generated by the following variables. You initialize variables in your given quiver, and you now start mutating arbitrarily to any vertex that you want. And for each of the quivers that you get, for which there are typically infinitely many, you gather that set of variables and you throw it in the generators. And the relations are exactly these ones. So for instance, x1, x2, x3, x4 is the first sort of people in the generating set. And then after doing that, you throw in x1 prime. After mutating here, you're going to throw in x3 prime. And now for any sequence of mutations, you always keep throwing in the new extra guy that you're updating. Typically, this doesn't end, meaning you're going to get infinitely many people who are actually always new. Sometimes, and here I put an example, so if you have the variable x and the variable y, but by the way, if there's no arrow going that way, this product means 1. That's why the 1 plus y in there. So if you do this 5 times, me 1, 2, 1, 2, 1, then you're going to go back to the same thing. And in this case, the total number of variables that you obtain is finite. So that's kind of a really nice case. The finite cluster algebras are classified. There's an AD classification, which means it's very beautiful, they're great, wonderful combinatorics, but it's very rare. It's not very common. So typically any random quiver that you choose is going to be of infinite mutation type. Okay, is this purely combinatorial / algebraic interlude? All right. Okay. Good. So now,
I don't know, it might be a bit early. So I guess it is known that you keep going from xi to xi prime. There's a rational function involved there,
right.
and I guess it's known that this always has positive coefficients.
Well, that's
Yeah.
that's the positivity phenomenon that was proven.
Yeah. Does that have anything to do with you have to choose like a positive braid or something?
Oh, I don't think it has to do with the general positive rate. I think it has to do, and that's the way GHKK proof did this kind of positivity things. It has to do with the fact that at the end you're counting something.
Yeah.
You're counting holomorphic disks or broken lines. You're doing some count of something which is positive, it's an actual number, and that's sort of the geometric reason why these coefficients are positive. But it's sort of not.
I guess the way that it is kind of affecting Q, that is this theory going from the understanding Lagrangians and the Lagrangian fillings, how many that seem to be looking like a positive braid. Is that like just irrelevant to the fact?
So tomorrow, lecture 2, I'll say this theorem should be true without the beta in there. The whole theory should run for any Lagrangians, and I'll explain what are the issues that we cannot prove that, but morally, I see no issues why this shouldn't be true. Like the geometry tells you something very close to that should be true, if not exactly that. So I don't see that much with the positivity of beta. Okay, let me point out something in this, both in that world and this world. Notice this statement about being globally regular. Highly non-obvious from here. When I write x1 prime, or when I've done one of these merodermies, I get a denominator. And when you do it one time, you kind of compute and you realize, actually, every time this guy is 0 and this is 0, every time this guy is 0, this the numerator is also 0, so this actually is regular with my constraints. And you can start playing with the flags and it's fine, but it gets absolutely insane. It gets to a problem of, I want to show that if this flag coincides with this other flag, then this flag and this flag plus this flag with this flag, for this piece of this flag and this other flag, they don't also coincide. And that's sort of if the denominator vanishes and the numerator vanishes. So that would be sort of the hands down proof that these things are regular. It will be like a really serious transversality problem for flags, which is how I did it initially, and it was kind of a pain in the neck, and then we found a better proof. So that never mentioned flags, at least not so bad. Okay. Is that clear so far? So now what I want to discuss is how to prove this theorem, and why on earth do these formulas appear coming from geometry. I'm going to erase, I'm sorry, that's a state we're in, but I have to erase this. Is it all right? I always tell my students, don't erase the theorem that you're going to prove. Okay, but I'm going to do exactly that. So now we're going to do exactly the same thing and just justify what are the steps of this proof. So the number of steps, I always try to keep it as geometric as I can. So this is a proof of, or sketch of the proof of this thing. So the first thing is the starfish level. So, yeah,
Just want to make sure, so you only change the coordinate for fine.
the only coordinate that changes is the one associated to the vertex that you're meeting. Correct. That is correct. Yeah. So that's not true for X mutation, by the way. But, it is true for this case. Okay. So the first thing is understand, because that's where all this business is coming from us. It's coming from the uncompressing system. So understand how an uncompressing system goes through a Lagrangian surgery. Undergoes the mutation mu sub lambda and mu sub d, and this is understood as a symplectic topology operation. As Lagrangian surgery on D. On L at. Does that make sense? So that will be the first step. I'll be discussing that second. The second thing is effectively what you're going to be wanting to prove is that okay, so to show that this with the lambda in here, I'm going to stop putting the piece, that this is isomorphic to this cluster algebra. So let's just write this A, that's how it's usually written. So A associated to the quiver Q, that is associated to the linking, to the intersections of the boundaries of these uncompressing systems. You want to show, we want to argue that the given L, the given filling that you have, union the once mutated ones actually cover. So let me explain that slowly. We want to argue that T sub L union, and now I'm going to write everybody mutating these guys. So T sub mu d1 of L union dot dot. So all the mutated people, assuming it's a maximal system. So then I get 2G of L in here. G is the genus of L in here. So I take these tori, that these guys are an open cover of my manifold. So these guys, open cover of my space. So this is a very geometric statement. Like I'm not talking about cluster algebras or anything. So what's happening here is I have my space and of lambda, then I have a filling, L. Okay, that does not typically cover the whole space. The whole space is not birational to a torus, typically, I mean, or a offlink or something like that. And, but you can say, well, let me add T sub having mutated at the first coordinate, mu1 of, let's call it mu1 of L instead of T sub 1. And now I can also add the torus chart mutating M2 of L, and so on. So I just add the ones that we call them the adjacent torus, because those are the ones corresponding to exactly mutating a one vertex from your initial seed, the seed being the Lagrangian and compressive systems, which is say quiver and their variables. And what is this geometrically? Sorry, what is this algebraically? So you want this so that this ring of functions is isomorphic to this cluster algebra. But if you think about it carefully, so this is a compressing system, what did you learn in algebraic geometry? Two varieties that have the same ring of functions, what can you say about them? Can you conclude that they're isomorphic as affine varieties? Okay, let's start easy. If I have two algebraic varieties and I know their fields of rational functions are the same, what do you know about the two guys? You know that there's an open set, this is birational equivalence, right? Now, if you know that the rings of regular functions coincide, then you cannot conclude that the varieties were isomorphic as algebraic varieties, but you can do so up to codimension 2. Wonderful. This is Hartog's theorem. So you only need that up to codimension 2. So I always write these in the papers, kind of the equality means up to codimension 2 on top of here, and this is because of Hartog. So the codimension 2 phenomena, it's because of Hartog's. There's an algebraic version of Hartog's theorem called Hartog's theorem says if I have an homomorphic function on say Cn, which is homomorphic away from a codimension 2 set, it extends to an homomorphic. Typical example, if I have any function in C2, which is homomorphic in C2 except at the origin, then it must be homomorphic at the origin. So for instance, C2 and C2 minus the origin are two algebraic varieties which have the same ring of functions. So actually, because of that, this up to codimension 2 business actually suffices. Not to say this is not very interesting, but think about it the Hopf-link. What would you do with a Hopf-link? You would start with one Lagrangian cylinder, then there's a unique vertex. For the Hopf-link, there's a unique disk. That's the guy you're going to mutate at, and you're going to do it once, because otherwise it's impulsive. So you start with your Lagrangian cylinder, you mutate it exactly once. Now you've obtained your two torus charts. So remember that picture from yesterday, where there was this torus chart that went kind of from above, that was one cylinder, and then there was the guy who went from below, that was the other cylinder, so that was one C star, the other C star. And then we had that the variety was not just that, but there was also an extra point in here. So I'm just trying to emphasize for you, indeed, it cannot be true that the union of these equals that. Already in the Hopf-link, the union of the green and the orange, green and orange, does not see the red point. That's fine because of Hartog's. So it suffices to compute that. And then finally, so 2 shows the following. So step 2 shows that your algebra, so it will not exactly show that. Well, I should have been more precise. So this is U, which is very close. This is called the upper cluster algebra, which is the algebra generated by the first tori and then the adjacent one. So step 2 shows that there is an inclusion of the algebra that we wanted, A, K of T, inside my ring of functions, U. I mean, maybe I should just write this. So because this includes in this, and this is isomorphic to this is M lambda. And now the last step, which is kind of a nice one, especially from the wave viewpoint, but it's a non-trivial one, you need to argue it, is that actually the reverse inclusion holds. So to show the other inclusion, so to show the inclusion that goes the other way, that's the one that you're interested in. This here's what you do, it's a very geometric thing, is you coordinatize this guy, you find generators of these people, and then you show that every generator in here actually belonged in here, and then you're done. So how do we do this very, very explicitly? This is actually how we prove it in the paper, is how do we coordinatize this guy? So from James's recitation today and Casals lectures yesterday, remember the set of variables zi's. So this guy was thought of as being inside of some space z1, and then z, you have as many as the crossings of beta, remember that? Now, as I'm writing things, this is an inclusion of varieties. Now, what that means at the level of rings of functions, it means this ring of functions is given by polynomials modulo some ideal, the ideal that cuts out that variety, right? So what you want to do is to show that each of these zi's actually is already in here. Which is to say, you want to show that each of the zi's, which you can think of as red chords, was actually, because think about it from the augmentation viewpoint, a red chord is a function on the augmentation parameter. You want to show that each such red chord, each such zi, is a cluster variable for something. And now let's do all together steps 3, and then the more elaborate thing will be steps 1, and maybe we'll come into 2. From the computations that James did today, and from some of the things you've seen, what do you know that will get you, what kind of weave do you know that will immediately get you the zi as part of the cluster variables in your weave? Remember this morning, or James, remember? If you start, the way James put it is, he said, if the arm of the trivalent on the right goes till the end, that's a zi. Another way, maybe easier to say, is that if the very first thing you do in your Lagrangian filling is a d4 minus, then the right-hand side zi is the cluster variable for this d4 minus, because it's measuring the transversality between those two flats. So what's the trick? The trick is that given any of these zi's, you just build a filling that the first pinching move is exactly that guy, and then you're done. Then that, because that produces the clusters. So that's how it's done. And the way you use that rigorously is the cyclic rotation. You always show, if I pinch the first from the left, that's a cluster variable. But if I wanted the fifth crossing to be like that, I do cyclic rotation, I pinch there, and then I conjugate back. Does that make sense? So maybe it's not, because of the way we've built things, not as surprising that every chord does appear as a cluster variable in some seed. I'm not claiming that there's one seed that contains all of them. There's, for each of them, there's some seed that contains. There's many seeds that will. Is that clear so far? All right. So now we're going to go down to the geometric part for the last 5 minutes, which is how does the outcompressing system change? And I promise, I mean, deep down, you already know that. Not because I told you, because I think all of you know the word dead twist. So here's a nice lemma. Position here, proposition. In a Lagrangian surgery, and this is a local model. So in this Lagrangian surgery, mu sub d, you can draw this. You have L in here. You have the disk D. So this is D in here. This is L. And now we're going to consider 2 curves. First curve goes out like that. Let's call this gamma plus, intersecting it positively, and then gamma down. It's 1, okay, gamma minus. All right. So then the statement is, as you do Lagrangian disk surgery, you understand how this changes very well. So M sub D. The one that intersected negatively doesn't care about it at all. And maybe I should be clear. So let's orient it this way. And now this guy stays the same. Now I should give it another name. I should give it something like gamma minus. So let's be precise. Mu sub D of gamma minus is gamma minus. So that's the state. That when I go under here, this stays the same, and this new curve keeps bounding the Lagrangian disk on the complement. An interesting thing is that this guy twists around this guy, and then it comes back going up. So the statement is mu sub D of gamma plus is, well, this curve, which at least homologically you can think of as the old gamma plus the thing that you're mutating now. How is this formula called? Somebody say it though. The Picard-Lefschetz forms. There's many ways to prove that actually in different papers. People ask me these like I don't know, it's maybe hard to find in the literature, but I've written like 3 different formulas in 3 different papers. And so why is this true? It's very simple if you think, for instance, in terms of a Lefschetz vibration. On a Lefschetz vibration, you know the monodromy around the point is exactly given the then twist of the vanishing cycle, right? And we've maybe talked or you know about that the difference between the Clifford and the Chekhanov torus is exactly crossing a critical point. So what you're going to undergo is a then twist. Now, there's a subtlety, because this is a Lagrangian and not a symplectic Miller fiber, about the fact that only the ones that intersect positively will actually intersect, and the other ones won't do it. But that is the statement, and there's this kind of Picard-Lefschetz formula, and it tells you how these disks do change. So an uncompressing system here, D stays was an uncompressing system. It's uncompressing. Stays uncompressing under mutation, u sub d of this is uncompressing if nothing bad has happened. So if that is the big if no bindings in the original. So if here you had 2 curves that share a bigon, so if this orange guy had created a bigon with D, the boundary of D, then once I then twist it, what's going to happen to the orange? Well, imagine there was a bigon like that. Then the orange is going to go like this, intersect itself and go up. That's going to create an inverse form. You don't want that. So if you had no bigons on this D, then you're good to go. And then, yeah.
So is it supposed to be a left-handed Dane twist?
Oh,
Okay.
It's supposed to be a positive.
Okay.
Yeah. I wasn't super careful with the orientations. Yeah, it's a positive then twist.
Well, actually, mapping class people say the left-handed is positive. But...
Oh, then it is. Sorry.
No. The thing in a left chest is a right-handed Dane twist.
Yeah, so that the one
Yeah.
in the left is vibration.
I'm just saying mapping class people
Oh, I see.
frequently say the other one.
Okay, good. Okay, so out of this geometric computation about curves and surfaces, out of these, you deduce the formula that was here about how the monodromies, change under use of D. So general Lagrangian researchers. There's 2 ways to go about it. You can be like kind of brutal about it, just like brute force, imagine a very complicated scenario, but there's also a trick, which is if you're in a weave and you have a very complicated tree, there might be a lot of things, but one thing you can do if you have a wide tree is you can do weave equivalences to move it down to a unique short segment, and then the formula is completely obvious for the short segment, because it's just a wide and move. So you prove it there, and then you kind of undo it. Does that make sense? Okay, so in the last couple of minutes, I just want to hit the just press buttons.
There you go.
So I just want to illustrate something for you, which is if you have an actual weave, you actually can have a sense of whether it's going to have infinitely many fillings or not, just by studying the quiver to begin with. And then if you don't still know, by then you can study the variable associated with the quiver.
Okay.
So you need to log in.
Yes.
Okay, so again, what would the sort of working mathematician's approach to this would be? You have your braid, at least for braids, so start with your braid, you go to the app in Dapping's website, you draw your favorite wave, you click it, and then remember, it gave you the Lustig cycles, it gave you your variables, but it also gave you that quiver on the right. Remember that I said that this morning? So now you take that quiver that comes out of Dapping's website, and now you're going to plug it in, sorry, this is not integrated, into another app, and I'm now going to show you. And now the other app is going to be very good for mutating stuff. And this is an app by a Swiss mathematician, Bernard Keller, he's in Paris. And this app allows you to mutate the quiver itself, which is what I'm going to show you now. But there's a slight, how do you call this? Like there's a slight feature that allows you to also keep track of the variables. So you do what I always do, Google his name, the non-killer. Fine, that's him, very nice guy. Okay, we organized a workshop together in. Cannot see, why is it only half? Oh, good, so, yeah, we organized a workshop tour over Wolfpack about 2 years ago. It was like a lot of fun. It's really nice. So you can download this, but you can also do it online. So for instance, you can take whatever quiver you want. So remember, you go to Dapping's app and you get a quiver. So now you go here and you implement it and you start adding nodes. I add this node, this node, this node, this node, a bunch of nodes in here. And now you add arrows. I don't know. Like I'm making one up as I go, but you can imagine that you've gone to Dapping's website and let's see. Doesn't have to be very complicated. Already pretty small quivers do the job. And if you want to do 2 arrows, you can also do that. For instance, you can 3, 4, 3, 4 again, and that's it. You can make it later like that if you want, and any way you want. Are we happy right now? Okay, so I'm not going to show you that, but there's when you download it to your computer, you can also say add variables, and it will add the xi variables in each of the vertices. And now I'm going to start mutating, and it will mutate for you the variables. So so let me just zoom in so you can all here. So this is the guy. This is the quiver we're trying to mutate, and you want to know, does my Lagrangian have infinitely many fillets? So if you black box the theorem that I proved with Concao a year and a half ago or something, the theorem says that any mutation that I do algebraically through that process can actually be realized in the Lagrangian setting. Well, one way to say that is no bicons will appear, and if they do appear, you can get rid of them. So that's a non-trivial statement. There's some work and interesting things behind it, but once you use it as a black box, you can just go to Bernard's app and start playing. Okay, I mutated 1. For instance, let's mutate at 2. What's going to happen to the arrow? Flipped, no problem. What about 7? 7 will add an arrow from 6 to 8, and then those 2 will flip. Look, an arrow from 6 to 8 and the 2 to 7 flip in there. And now you're like, okay, let's mutate here. Whoa, that was pretty elaborate. This one, well, that's not too bad. Not too bad. Created 2 here. Not too bad. Oh, this is not doing much. And then once you get bored of doing that, you can say random. Just do 5 mutations. So you go here and you say, give me 5 mutations. Goes there. Okay, nothing has happened. Give me 25 mutations. This has happened. Okay, let's go crazy. Give me 10 more. This is happening. And now you can keep doing that. For instance, give me 100 mutations. Oh, I'm going to collapse this. Maybe I'll just do this one. Yeah, so here, for instance, I mutate 1, you can kind of keep mutating like that. Yeah, curves. Yeah, so let's be modest about it. So 10, okay, 10 again. Let's do 15 again. Let's do 15 again. Now this is what I want to show you. Typically, what's going to happen? The thing doesn't collapse. Still thinking about it. What's going to happen is that the numbers are going to increase very, very fast. And so, what is this saying? This is saying the L-compressing system that's being carried through that Lagrangian surgery has curves on the boundary that intersect whatever this number is a number of times. So the intersections, and they're all positive intersections, they get completely wild, and just out of the number of intersections of the L-compressing system, you can already tell them apart. Now, in some cases, it's not sufficient to tell the quiver apart. The quivers might be finite. This happens for the cases with 3/6 torus length. There's finitely many quivers, 5,000 something. But if you now keep track of the cluster variables, there's actually infinitely many. So that's, James, you're not agreeing if there's 5,000 something? Yeah, I think okay. There's some number of finite, there's many cases in which there's finitely many quivers, but the variables are infinite. So that would be your second way to check that it's infinite. All right? Okay, well, let's take a break then.